Hello, and thanks for joining me. Today we are going to start talking about the mathematics of chemistry. We're going to start talking about the tools that we use mathematically in order to do some of the chemistry that we're going to be doing. So we're going to be taking a break a little bit from chemical reactions and chemical formulas. And we're going to talk just about math for a few minutes. And to start off with, I want you to remember measurement and how we take proper measurements. If you want to go back and watch the video I made about how to take proper measurements, that wouldn't be a bad idea. But you need to remember about how to take a proper measurement with the precision and that last digit being a guess. That's very important to what we're going to be talking about because we're going to be discussing today significant figures. And what significant figures are a way to deal with the data that we collect in lab. Pretty much all the data that we collect comes from measurements. And as we talked, measurements have error. Measurements all have error because we make that guess whenever we are looking at it. So you have the last measurement that your tool gives you, and then there's that extra digit that we make a guess because of the uncertainty in the measuring device or the measuring tool that we're using. So because we make error when we make our measurements, we have to account for that error whenever we use any measurements that we have. All right, the smaller that guess is, the smaller our error and the more precise or repeatable our measurement is. So if you've got a measuring tool that has tick marks every centimeter, then your guess is somewhere within the size of a centimeter. But if you have a measuring tool that has tick marks every millimeter, every tenth of a centimeter, then your guess is somewhere between those millimeters, so in a tenth of a millimeter size. So the more marks that you have, the closer they are together, the smaller your error is, and therefore the smaller your guess is, and the more precise or the more repeatable your measurement can be. So if I have the examples here, we have 2.84 or 28.4 grams and 28.401 grams. Either way, we could say something is 28 grams. That would be our rough estimate. But this measuring tool says that the 4 is our guess. The 8 is the known digit. We know the ones place, and our guess is in the tenths place. Well, on this one, our last known digit is the 0. So we know the hundredths place. So we're accurate to the hundredths place, and our thousandths place is the guess. So this is a 1,000th of a gram is our guess, and this is 4/10ths of a gram. There's 100 times difference in that guess. So this guess is much smaller, therefore this is a much more precise measurement. It's a much more precise recording of it. So it's all based off the tool that we use. So again, go back and watch that video on how to take proper measurements way back at the beginning of the course. So the number of digits that you have tells us the precision. The more digits that we have, especially after the decimal place, the more digits that we have tells us the precision of our measuring tool and the precision of our measurement. And when we use those measurements, we have to account for that precision when we record any of our measurements. So any measurements that we take in the lab, we have to account for the precision of those measurements. And that's where significant figures comes in. That's what significant figures are. They're a way of showing the precision of a measurement when we use them in calculations and carrying that precision through in our calculations. And we'll get to that in a few minutes. But when you're dealing with measurements, there are rules for determining whether or not a digit is significant. Okay? So I'm going to go over these rules, the rules for determining if something is a significant digit or not. Now, point of order, something you need to make sure you understand before we go any farther. If a number is not significant, that does not mean it is not important. Just because something is not a significant digit does not mean it's not an important digit. I personally think that we should use a different word than significant figures or significant digits for this, but I don't get to make the rules. I don't know who decided it, but because we oftentimes confuse the word significant with important. We talk about our significant others and the important people in our lives. We use those words interchangeably, but when we're talking about it here, significant and important don't necessarily mean the same thing. So That's what you need to make sure you understand. I want you to think about your paycheck for a minute. If you were doing a job and I say I'm going to pay you $1,000, okay, and then I give you a check at the end that has a 1 and 3 zeros, that's important because that's $1,000. All right, so those zeros are important, but from a significant figure standpoint, those zeros are not significant. So if I were to just give you only the 1 is a significant. So the 1 is the significant digit. The 3 zeros are not significant, but they are important because without those zeros, your paycheck is $1, not $1,000. Hopefully you understand the point of the difference between significant and important. Just because something is not significant does not mean it is not still important. We call those placeholders, and as a general rule, placeholder digits are not significant, but they are very important because they tell you the value of the digits that are significant. So that 1 in the 1,000 is a significant digit, and the zeros tell you the size of that 1. They tell you that it's 1,000, not just $1, it's $1,000. So those zeros are important even though they are not significant. They are placeholders. It's telling you the value of that significant digit. That's why we call them placeholders. So we're going to discuss the rules of significant figures now. These can be a little confusing and complicated, but bear with me, I have a little trick for you at the end. All right, so rule number 1, any non-zero digit in a measurement is always significant. So when we take measurements, we only record the digits that are part of the measurement. So any non-zero digit is always a significant digit. So if I have this number, 87.5490400 kilograms, that's a very precise measurement, by the way. I've got a lot of decimal places here. My guess is way over here. There's lots of digits here. It's a very small guess. So this is a very precise number. However, the significant digits are, from this rule, the non-zero digits are the significant ones, the 8, 7, 5, 4, 9, 4. Those are all significant because they're not zero. So non-zero digits in a measurement are always significant. That's rule number 1. Rule number 2, any zero between two significant figures is also significant. So the same number, we have this 0 right here. It is between a 9 and a 4. Well, the 9 and 4 are not zero, so they are significant. And therefore, any digit between them has to be significant also. You can think of it as you're significant by association. Because I am between two significant figures, I am also significant. So this 0 is significant because it's between two significant figures. So back up for a minute. Rule number 1 says that all digits that are not 0 are significant. The rest of the rules are all dealing with when is 0 significant and when is 0 not significant, because zeros are sometimes significant and sometimes not. Any digit that's not 0 is a significant digit in a measurement. Okay, so rule number 2 is the first one that deals with zeros. Zeros between significant figures are significant. Rule number 3, leading zeros are placeholders and are not significant. As we discussed a few minutes ago with the paycheck, placeholder zeros are not significant. They are still important, so they still need to be written down, but they're not significant. They don't show the precision or the accuracy of our measurements. They're placeholders. So leading zeros, what do I mean by a leading zero? Well, that's a 0 in the front of a number. It leads all the other numbers. So leading zeros are the zeros here in front, all right? The ones you're only ever going to have leading zeros when you've got a number that's smaller than 1, because you've got that 0.000. You've got the decimal and zeros in front. All of these zeros are not significant because they're leading zeros. All they're doing, they're important because they're telling you the value of that 8. Without these zeros, this would be a very huge number. You've got 875 million. So this would be 800 million is the place if these zeros are not there. So these zeros are very important because instead they tell us that it's 8 millionths of a kilogram. So those zeros are important for telling you the value of that 8, but they are not significant for showing us the accuracy or precision of our measurement. That's rule number 3. Rule number 4 says trailing zeros are only significant if the decimal is present. So trailing zeros would be zeros that are following after the numbers. So in this example, 875490400 kilograms. So these trailing zeros are not significant because the decimal is not present. So if the decimal is present, these would be significant, but they're not. What this means is these are just telling us the value of that 4, that 4 is in the hundredths place. But what this tells us is that these are not significant, so this 4 is actually our last known digit. So, but it's telling us that it's 400. It is our place value. So they're not significant. They're not showing us the precision of our measurement, but they are showing us the value of that 4. So they're not significant. These zeros, however, because the decimal is present, what they're telling us is that when we make our measurement, this is our guess. Our known digit here is 0. This digit is our guess. So we're telling us the precision of our measurement. Without these zeros, our guess is in the place where this 4 is. But with these zeros, our guess is 2 spots over. So it's a much more precise measurement. So these are significant because they are telling us the value of our precision. And that is what significant figures are all about. Significant figures are about telling us the precision of our measurements. So these 2 zeros are significant because they're telling us the precision of this measurement. These 2 zeros are not significant because they're not telling us the precision of our measurement. All they're doing is telling us the place of that 4. Rule number 5, and this is a big one. Significant figures only matter for measurements and calculations in which measurements are used. So when we're making measurements, any measurement that we take, we have to account for the significant figures. And basically, we are going to write down all the numbers from our measurement, and whatever we write down from our measurement is a significant digit because we're only going to write down the significant digits. What's important is when we use those measurements in calculations, we have to know how many significant figures there are so that we can account for that when we do our calculations. But significant figures only matter with measurements and calculations used in measurements. So what do I mean by that? Things like counting numbers or multipliers or accepted constant values are considered to have an infinite number of significant figures. So we basically ignore their significant figures. And we say they're an infinite number, you'll see, because when we do calculations, the number or how we deal with our significant figures always deals with whatever's the fewest number of significant figures. So we say they have an infinite. So no matter how many significant figures my measurement has, a constant or a counting number is always going to have more because it's an infinite number. So when I say a counting number, that would be like I have 12 of something. If I'm going to multiply something by 12, a multiplier is a number that does not have significant figures. Okay. So how do I tell if something is a measurement or not? Because again, rule number 5 tells us that significant figures only matter for measurements and calculations done with measurements. So how do I tell if something is a measurement or not? All right, a measurement is always going to have a unit, always. Because if it doesn't have a unit, it's a meaningless number. All right, in mathematics, we just use numbers to do things. But in science, our numbers all have meaning. They represent actual objects, actual things. So I can't just say 12, I have to say 12 grams because 12 grams actually has meaning. The number 12 is just a number, and numbers are abstract. They don't have any actual meaning in and of themselves. So 12 grams means something, but without the unit, the number is pointless. Okay, so a measurement is always going to have a unit. Counting numbers, multipliers, and coefficients don't have units. So if I'm just multiplying my measurement, if I have 58.6 grams and I'm going to multiply it by 2, that 2 is a multiplier, so it doesn't have any units. My grams measurement is the one that's the measurement. The multiplying by 2 times 2 is not a measurement, it's just a multiplier. And the coefficients of our balanced chemical equations are numbers that do not have significant figures. They have an infinite number because we're going to ignore them. Accepted scientific constants do have units, But as constants, they have infinite sig figs. And we treat them as infinite sig figs because even though they were calculated and arrived at by measurements that were made, we're going to now, the scientific community has accepted this constant as the accepted value of something, so we're going to ignore it. So, for example, the atomic masses on the periodic table. Oxygen has a mass of 15.999 grams per mole. It has a unit of grams per mole, but that 15.999 is an accepted scientific constant. So we're not going to deal with how many significant figures it has, just because it has a unit though, but because it is in a scientifically accepted constant, we're going to ignore it. It's kind of hard to tell sometimes, but you would know if we're dealing with a constant or not. If it's a number that is given to you as something that's always the same, like the mass of oxygen or the acceleration due to gravity, those are scientific constants that are accepted values, and so we do not account for their significant figures when we are doing calculations. In chemistry, the numbers that we're going to deal with the most that are going to be constants are going to be the masses on the periodic table. Those are going to be the constants that are going to be the most used constants for this application. The other numbers that we're going to be using a whole lot that are not significant figures, that we don't deal with their significant figures, are going to be the coefficients of a balanced chemical equation. So there is a trick to doing this. There is a helpful way of helping you remember, instead of memorizing all of those rules, to be able to look at a measurement and know which digits are significant and which ones are not, so that when we're doing calculations, we can account for the proper number of significant figures. There is a little tool, and I'm going to use a map of the United States to help us with this. So this does help if you have a little bit of an understanding of basic geography. Over here on the left side of the United States, or the west side, would be the Pacific Ocean. And over here on the right, or the east side, is the Atlantic Ocean. All right, the P and the A are the important part here. And so I'm just using this to help us identify how many significant figures something has. If the decimal is present, we're going to start on the P side. If the decimal is absent, we're going to start on the A side. So you'll see, if you go back and look at the rules, that for the most part, whether or not a zero is significant kind of depends on the decimal, if the decimal is present or absent. So if I write the decimal or not, is going to help us determine which things are significant and which things are not. So how does this tool work? We're going to write the number that we're dealing with in the middle of our United States. So let's use this one, 0.05600 grams. Now, I want to know how many significant figures there are in this number. So I ask myself, is the decimal present or absent? Well, the decimal's right here, so it is obviously present. All right, so since the decimal is present, we're going to start on the Pacific side, or the left side of our number. And we're going to go from this side over, and when we get to something that is not zero, this 5 is not 0, I'm going to start counting, and I count everything. So 1, 2, 3, 4. There are 4 significant figures in this number. Again, these zeros are not significant because they're leading zeros. But if you don't remember the rules, we know that the decimal is present, and so I'm going to start over here on the Pacific side, and I start counting when I get to something that's not 0. And then I count everything. I count all of the digits. Now, the G is a unit. It's not the digit. So this is 1, 2, 3, 4 significant figures. Let's look at this number. Now I have 105200. Okay, so 105,200 grams. Well, my decimal is absent. There's no decimal here. So the decimal is absent, so we're going to start on the Atlantic side over here. And I'm going to start counting when I get to something that is not 0. So I start here at the 2. So this is 1, 2, 3, 4. So this digit or number also has 4 significant figures. Now again, these zeros are trailing zeros, so they are not significant because they come after the last non-zero digit. They're trailing zeros, but if you don't remember the rules, I know that the decimal is absent, so I start over here and I don't count anything until I get to something that is not zero. So 4 significant figures here. Let's do this one. Now, it's the same number, except this time the decimal is present. So we're going to start over here on the Pacific side. So I start over here and hey, look, that one's not 0. So 1, 2, 3, 4, 5, 6. I count everything. Once I start counting, I count everything. So there are 6 significant figures in this number. Now this is exactly the same number as the other one you say. This is 105,200. The other one was 105,200. But the difference is that decimal. This decimal is telling us that this is our precision, is right here in the ones place. Whereas before, without the decimal, the precision was in the hundreds place. So this decimal is telling us the precision of that measurement, and therefore these zeros are significant because significant figures are telling us the precision. That's the important thing you need to remember. Now, when you're doing calculations with measurements, you have to account for that significant figures. You have to count for that precision. So the cardinal rule, the most important rule of calculations when you're dealing with significant figures, is when we make calculations with measurements, our answer cannot be more precise than our original measurements. So let's look at an example situation. So let's say I'm going to measure the density of this cube. And this cube has a mass and a volume. And I'm going to measure its volume using a ruler and measure its mass using different tools. So on this side, let's say I measure the mass of this with my son's toy balance. And I've measured the mass of that, and I get a mass of 8 grams. Then I take it up to the local university and I use their analytical chemistry lab and I measure their balance using their super precise measuring balances, and I get a measurement of 8.014327 grams. Not very precise over here. Very precise over here. All right, 8 grams, 8.0. Now, would you say that both of these are basically 8 grams? Yes, it's the same cube, okay? So I'm going to take these. Okay, so now I'm going to measure the volume of this using a ruler and multiplying it out. And let's say I measure it out and I get a volume of 5.632 cubic centimeters. Let's say that's the volume that I get with my measuring tool. So to find my density, I'm going to take my 8 grams and I'm going to divide by 5.632 cubic centimeters. So when I do that in my calculator, I do 8 divided by 5.632, and I get an answer of 1.4204544545. This is what the calculator gives me. How is that possible? This is an extremely precise number. Extremely precise, even more precise than this super calibrated balance gave me. It's a super precise number. But I used a toy scale. That doesn't make sense. Should I possibly get something that is this precise using a toy that is not precise? That doesn't make sense. Now, let's say it's the same measurement and I divide this side by 5.632. So now I have my 8.0143267, and I'm going to divide that number by 5.632. This time I get 1.42299834. Now, this is much more reasonable to get a precision like this from these measurements than it was from these measurements, because this was a toy balance and this is a super precise balance. And a super precise balance is going to give us a super precise answer. A not very precise measuring tool should not give us a very precise measurement. your answers, when you do calculations, must agree with the precision of the tool that you are using. So you need to round your answers in calculations to show the proper number of significant figures. That's the important thing that you need to understand. We're going to do our calculations and then we have to round our answers, because what your calculator gives you, the calculator is always going to give you the mathematical answer. It just plugs in numbers and does what the math says to do. But we are not dealing with just non-important, uninformed numbers. We're dealing with measurements. Our numbers have meaning, and so we have to give them that meaning through rounding our answers when we are dealing with our significant figures. All right, there are different rules for rounding when you're adding and subtracting versus when you're multiplying or dividing. So when you're adding or subtracting numbers, you're not multiplying error, you're just adding or subtracting numbers together. And so when you add or subtract numbers, you simply look at the decimal places. Your measurement will have the same number of decimal places as the measurement in the problem with the fewest number of decimal places. All right, so let's look at a couple of examples. So let's say I'm going to add together the numbers 3.05 grams and 8.0 grams and 32.56 grams. And I'm going to add these all together. It's very helpful, regardless of how a problem is given to you, if you write it like you learned in elementary school, stacking them up, lining up the decimals, and we add them together this way. It's also very important that you note they have to have the same unit in order to add or subtract them. If they're different units, you can't add or subtract. So I'm going to add these together. I have 5 plus 6 is 11, and that's 6 right there. And so 3 plus 8 plus 2 is going to be 13. And so that's 43.61. This is our answer, 43.61 grams. But this 8 right here only has 2 significant figures. It's only accurate, or precise I should say, it's only precise to the tenths place. So that means my answer can only be precise to the tenths place. These are more precise than this one is, and my answer cannot be more precise than my least precise measurement. That's the important rule. So I have to round my answer to the tenths place. So this number is less than 5, so I'm going to have 43.6 grams. This is the answer that I would give as the answer to my problem, because I used measurements and I calculated my answer. So I have to account for those significant figures. This number is the number your calculator will give you when you add them all together. But this is the correct answer, accounting for the significant figures. This is the precise answer. This is the mathematical answer. We always want the precise answer, the one that is given to us by the significant figures of our measurements. All right, let's do another example. Let's say I have 6,854.03218 9, and I want to subtract 56. All right, and since I need a measurement, we'll call these liters, and we want to subtract 56 liters. So I'm going to line up my decimals, the decimals right there, and I'm going to put this in. We have 6,798 point blah, 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 blah. So this is the precision of our first measurement, but a precision of our second measurement was only to the ones place. So I must round my answer to the ones place. I have to get rid of all of those extra digits because my precision cannot be more precise than my least precise measurement. That is the important rule for significant figures. So when we're adding or subtracting, we look only at the decimal places. Now when we multiply or divide, we're going to be multiplying our error. So if I have a tenth of an error, a tenth of a gram is my error, and I multiply that by 10, then my error gets multiplied. And so it's a much bigger deal. So instead of looking at just the decimal places, we're going to look at overall significant figures. Right? So your answer is going to have the same number of significant figures as the measurement in the problem that has the fewest number of significant figures. That's what's important. You always look at the fewest number of significant figures. All right, so let's look at some examples of that. So let's say I have the measurement and I want to do a density measurement. And so we're going to do 8.95 grams divided by 6 milliliters. And that's going to give me my density of in grams per milliliter. So grams divided by milliliters. There's my density is going to be in grams per milliliter. What's my answer going to be? Well, in my calculator, I do 8.95 divided by 6, and I get an answer of 1.491666667. And I scrunch that all together. Grams per milliliter. Now, this is a super precise measurement. This, not a precise measurement. This is even more precise than our more precise measurement. So my answer has to have the same number of significant figures as my measurement that had the fewest number of significant figures. So this number right here only has one significant figure. So my answer can only have one significant figure. So I look at this, and 1, this first digit is my significant figure, and next to that is a 4, so I'm going to round it off, and so I just am left with 1 gram per milliliter. Now, you might be thinking, but 9 divided by 3, this is almost 9, right? 8.95 is nearly 9. 9 divided by 3 is not 1. So why would I do that? Well, this is not a very precise measurement, so I'm not going to get a very precise answer. This is also why it's very important that you take as good and precise measurements as you possibly can when you're doing labs and doing experiments and collecting your data so that your answers make sense with the data that you collect. But if I have a not very precise measurement, I'm going to have a not very precise answer. It's not going to be mathematically correct. It is going to be scientifically correct. Those are not always the same thing. So let's look at another example. So I have 5.6372 meters, and I travel that far in 8.463052 seconds. All right, so this is my calculation for my speed. And so I'm going to put this in my calculator, 5.6372 divided by 8.463052, and I get an answer of 0.6660990826, and meters divided by seconds would be meters per second. So this is my mathematical answer from what the calculator gave me from dividing these two numbers. Now if I look at this, this number has 1, 2, 3, 4, 5 significant figures. And this number has 1, 2, 3, 4, 5, 6, 7, 8. That has 8 significant figures. Well, 5 is less than 8. So my answer has to have the same number of significant figures as my number in the problem that had the fewest. My fewest number of significant figures was 5. So 1, 2, 3, 4, 5. Remember, the leading 0 is not significant. So this is my 5th significant digit. Okay? So I have to look next door, and this digit is bigger than 5. So I'm going to round this one up. So I'm going to have 0.666, and that 9 is going to get rounded up to a 10. So this is 1, 2, 3, 4, 5 significant digits. I'm going to put my placeholder 0 in the front and my unit meters per second. So even though this number with all of the things is the mathematical answer I get from the calculator, this is the scientifically correct answer based on the significant figures of my measurements in the problem. Now, if you're dealing with both, types of calculations in one problem, then you have to follow the order of operations and round as you go. Say we have 5 plus, or we'll say 5 grams plus 8.3 grams divided by 12.4 milliliters minus 8 milliliters. So this is the problem, and I want to know, this is grams divided by milliliters, so I'm looking for density. And so I want to know this, but these are my measurements. And so I have 5 plus 8.3 grams. So I'm going to do 5 plus 8.3, and that gives me an answer of 16.3 grams. Mathematically, this is what the calculator gives. And then I do 12.4 minus 8, and I get 4.4 milliliters. Again, this is what the calculator gives me. And I'm doing the order of operations, so I'm doing my parentheses first. So I added these together, but I have to account for these significant figures. This number only has the ones place. This one has the tenths place. My answer has to have the same number of decimal places, because I'm adding the same number of decimal places as the number with the fewest. So this has 0 decimal places. This one has 1 decimal place. So my answer has to have 0 decimal places. So instead of 16.3, I should be writing just 16 grams. And this one, I have 1 decimal place, and here I have 0 decimal places. Same thing. My answer should have 0 decimal places. Now, that means I'm going to write down simply 4 milliliters. So I rounded my answers to the proper number of decimal places before I do the next step of my math, before I do my division. Now 16 divided by 4 is 4 grams per milliliter. So I get an answer of 4 grams per milliliter. Now I'm going to put this in the calculator just the way it is here, where I type it in as 5 plus 8.3, and I'm going to divide that by 12.4 minus 8. When I type it into the calculator exactly as it's written right here, I get an answer of 3.022727727 continuing. Now, 3.0224, those are not the same, but this number is mathematically the correct number, but this number is scientifically the correct number. This accounts for the error in our measurement. The calculator answer does not account for the error in the measurement. Our answers for any calculations have to account for the error in our measurements. So 3.022 is the mathematically correct answer, but it is not the correct answer based on these significant figures. That's the important thing. We have to round our answers based on the error and the inaccuracies and the precision of our measurements. So let's talk about this rounding rules, because I've found over the years that a lot of people don't really know how to round numbers properly. So rule number 1, you determine which place you're going to round to. All right? Rule number 2, you look at the digit to the right of where you're rounding. If the number is 5 or larger, then you round up. If it is less than 5, you leave it alone. Rule number 3, if the place you're rounding to is before the decimal, then the places between that number, the number in question and the decimal become zeros. If the place you are rounding to is after the decimal, all digits after this number get dropped. Okay, so let's look at some examples. So let's say I have the number 4.563200401 grams, and I need this to be rounded to 4 significant figures. I want 4 significant figures. Well, I start over here. This is 1, 2, 3, 4. This is my 4th significant figure, so I'm going to look next door. This number is less than 5. So that means the 3 is going to stay a 3. So now I have 4.563. Now I need to decide, what am I going to do with all of this? Well, since all of these numbers are after the decimal, we simply ignore them. They're not there. Because if I write zeros here, those are now significant figures, because remember, trailing zeros are significant if the decimal is present. So I'm not going to write them down. I simply just write down the unit. So I have rounded this off to 4 significant figures. Now let's take the same number, and this time I want to round it to 2 significant figures. Well, 4.5, there's 1, 2, and now I look next door. This is bigger than 5. So that means this 5 gets rounded up to a 6. So this becomes 4.6 grams. And again, since these numbers are all after the decimal, they're all going to just disappear. Okay? So let's look at a situation where they're not necessarily. So let's say I have 48059780009.463 kilograms. That's a really, really big number, very, very large mass. But I want to round this number to 3 significant figures. So I need 3 sig figs. 3 significant figures. So 1, 2, 3. This would be my 3rd significant figure. So I'm going to look next door. That's a 5. So the 1 is going to get rounded up, or the 0 is going to get rounded up to a 1. So I'm going to have 481. Now I need to decide what to do with all of the rest of this. All right. If I just write 481, again, think of this as your paycheck. All right. This is 48,059,780,009. If that's your paycheck, all of these spaces matter. If I round this to 3 significant figures, yes, this is 3 significant figures. I rounded correctly, but the problem is these digits all here are placeholders. Everything from the digit we're rounding to the decimal. That's 1, 2, 3, 4, 5, 6, 7, 8 places. I need to fill that in with zeros. And I do not write the decimal because now the decimal is not present. So these are not significant, but they are important. Because if you do not put those zeros, then you're telling me it's 481 instead of 48 billion. That's a really big difference. So always consider, do these places change the value? If I leave those zeros off, does it change the value of the numbers that are here? If I leave these zeros off, it's 400. With the zeros there, it's 40 billion. That's a big difference. So you need to make sure that you always pay attention to how you're rounding. We're dealing with measurements that have error, and because of that, we have to show the precision of our measurements when we are writing down our numbers, and we do that with things called significant figures. And then when we use those measurements in calculations, you have to account for the fact that those calculations have error in them, and so our answers are going to have error as well. That is the important thing that you always remember. Significant figures can be kind of scary. They can be kind of complicated, and it's a new thing because you're used to doing math with numbers, and it's just math, adding, subtracting, multiplying, and dividing. It's just doing math with numbers, and they don't really mean anything. Now we're going to be doing math with numbers that matter, and the numbers mean something. And so it's a little bit different, but if you pay attention, it's not super complicated. The math is still pretty easy. You're just adding, you're just subtracting, multiplying, or dividing, and then you're going to round your answer to a certain place. Just like when you were in grade school and you were told to round to the 10th place, you're going to round to the 10th place. The problem is, the issue is, your teachers and me and people who give you these problems, we're not going to tell you what place to round to. You just have to round to the place based on the significant figures of the numbers in the problem. So hopefully you got that. If not, watch it again. Go find some other examples somewhere online. Get it down. It's not super complicated. But again, thanks for watching. Have a good day.